Hi everyone, my name is Ke Xu. I'm a PhD student at University of Toronto Institute for Aerospace Study. I'm supervised by Professor Labro from the same institute and Professor Sullivan from Mechanical and Industrial Engineering, University of Toronto. I would like to present my research, which is separation control on a Naca 0025 airfoil using an array of MEMS-based synthetic jets. Flow separation on airfoil happens due to the adverse pressure gradient. Separation can even happen at low angle of attack in the low Reynolds number cases, where the airplane has shorter chord length and flies at lower speed. Typical applications that fall into the low Reynolds number range are unmanned area vehicles. An example of such laminar separation is shown in the figure at the top right. A separate shear layer can be seen over the airfoil, and a large vortex shedding in the wake of the airfoil. Once the separation happens, the aerodynamic performance is heavily affected. Even stall can happen. Therefore, we want to be able to control it. My study targets at controlling flow separation at low Reynolds number range. The chord Reynolds number and free stream velocity range is highlighted in the figure at the bottom right. Over the past 2 decades, many studies have tried to control flow separation using unsteady blowing, as this can effectively increase the momentum in the boundary layer, which allows the flow to overcome the adverse pressure gradient. An example of controlling the separation can be seen at the right. As the top is the baseline case, so no control is applied and the flow is separated from the airfoil, whereas the bottom one is a control case, forcing is applied and the flow has been reattached close to the airfoil surface. Many work have shown that the actuation frequency is an important parameter of the blowing, which governs the dynamics and effectiveness of the reattachment. The actuation frequency is often non-dimensionalized as F+, which is the frequency of the blowing times the chord length of the airfoil and divided by the free stream velocity. Actuation frequency at the order of 1 is commonly known as the low frequency actuation, whereas at the order of 10 is often known as high frequency actuation. As I will show later, these two frequency range have different effect in the flow reattachment. Another important parameter, momentum coefficient C mu, is often used to quantify the strength of the blowing. It's a measure of the momentum of the controlling fluid versus the momentum of the control fluid. For separation control on airfoils, it has been reported that the momentum coefficient needs to be greater than order of -4 to achieve separation control. Many flow control studies have used synthetic jet actuator as control device, as it can produce unsteady blowing with enough momentum at those frequency ranges mentioned before, while it does not require a source or sink of working fluid. Synthetic jet actuator comes in different exit geometries. The common ones for separation control on airfoils are rectangular, as can be seen at the examples at the right. However, the rectangular jet exit requires significant cutout on the airfoil surface. For safety concerns, it is not very likely to be used in commercial applications. However, smaller circular jet exit might be a potential solution. A previous student in the lab, Mark Fierro, has conducted successful control with a rectangular synthetic jet, which is shown at the top right. The current work is trying to use an array of circular jet to achieve similar control result as what he has achieved. With this smaller circular jet array, it can overcome the limitation of the rectangular jet exit and has higher potential for actual application. The experiment was conducted in a low-speed, low-turbulence wind tunnel in University of Toronto. The wind tunnel has a clear sidewall which allows optic access and flow field observation. The aluminum airfoil was horizontally mounted in the wind tunnel section. It has an aspect ratio approximately 3. The airfoil has 3 span-wide sections, and the midsection is hollow. It also has a rectangular cutout which houses the synthetic jet array. The airfoil has 64 pressure taps along its midspan, which allows pressure measurement over the airfoil surface. As we can see at the bottom right, the synthetic jet array has 2 rows, and each row has 12 synthetic jet actuators. The 2 rows can be controlled independently. In the current experiment, only the front row was actuated during the control. Particle image velocimetry was used to measure the flow over the airfoil for the baseline and control cases. 2 cameras was used to compose the field of view of the PIV images. 1,000 image pairs was recorded for each flow cases. The field of view sized 450 mm in length and 200 mm in height. Each field of view has 20% overlap in the middle, and the over resolution is about 10 pixels per millimeter. For the control cases, 8 phase angles was measured for doing the phase averaging. The phase angle is corresponding to the phase during an actuation cycle. For example, phase 0 corresponds to the start of the actuation, as the duty cycle of the actuation is 50%. The microblower or synthetic jet actuator used in the current research is very compact and quiet compared to the ones used for other flow control studies. It's about 2 cm by 2 cm and 2 mm thick. The carrier frequency it operates at is beyond human hearing range. It has been shown that this actuator can produce sufficient momentum for the flow control purpose, and it can also be modulated at different forcing frequency. By modulation, it means that essentially turning it on and off at a different frequency than its carrier frequency. Both frequency and amplitude response of this microblower was characterized using hot wire anemometry. The hot wire probe was placed at x/d equal to 5 to measure the jet centerline velocity. 3 microblowers were used for the characterization. The results shows that the microblower frequency response is right skewed. The peak is at 25.2 kHz. And we can see there is variation among the performance of the microblowers. Eventually, the carrier frequency of microblower was determined to be at 25.5 kHz. As this frequency, the amplitude response is smooth. Pressure distribution over the airfoil for the baseline and control cases are plotted in the figure. For control cases, the red points are from current study, and the blue points are from Fero's study. Notice that the same airfoil and wind tunnel facility was used in both experimental studies to make this comparison valid. CP of the baseline case suggests that the flow separation is near at 12% of the chord, with a lift coefficient of 0.189. CP of the control cases suggests the flow was reattached, with higher lift coefficient of the airfoil. The current experiment of the low and high forcing frequency was able to benchmark with the results of Mark Fero, as evident with the recovered pressure gradient and suction peak. Results from wake survey was plotted in the figure. The wake of the control cases is narrower compared to that of the baseline case. Notice the blue data points are from Vero's experiment for reference. It can be seen that the location and magnitude of velocity deficit has changed, which indicates the separation was suppressed. Drag coefficient was estimated using control volume approach, and it was found that the drag reduction can be more than 50% with forcing applied, compared to the baseline case. Velocity magnitude and streamlines of the baseline, as well as the control cases, clearly confirms that the separation was suppressed by the forcing. The black triangle on the airfoil represents the location of the jet that was forcing. For the baseline case, a recirculating region is seen over the airfoil, which represents flow separation. And for the control cases, this region disappeared, which represent the flow was reattached to the airfoil surface. Notice that the velocity for the control cases is averaged over 8 phase angles during an actuation cycle. For the low and high forcing frequencies, the mean flow appeared to be very similar. Reynolds shear stress for the baseline case clearly shows a separate shear layer over the airfoil. It indicates momentum transfer from the free stream into the separate flow and eventually into the wake. For both controlled cases, the separate shear layer disappeared, and the dominant Reynolds shear stress is much closer to the airfoil surface, which shows that the momentum transfer is mainly between free stream and the boundary layer near the airfoil surface. Also, here this flow quantity appeared to be very similar in the mean sense. In order to investigate whether the dynamics of reattached flow for both low and high forcing frequency is similar, contours of transverse coherent velocity is plotted for each phase angle. Blue means downward and red means upward transverse velocity. Vortex identification was also done by plotting isocontour of λ2 to find possible vortex in the flow field. For f+1, a closed contour of λ2 is at 0.8 c over the airfoil, with downward velocity at its downstream. This suggests that a clockwise vortex present over the airfoil. As the phase angle increases, the vortex moves along the airfoil, detaches from the trailing edge, and dissipates in the wake. The vortex emerges at 0.3 c along the airfoil. During a control cycle, the vortex induces downwash and which enhances the momentum mixing near the airfoil surface. For F plus equal to 11.76, instead of an individual vortex seen before, two layers of vortices are present in the reattached flow. The first layer is near the airfoil surface, and the second layer is entrained into the free stream. The first layer of vortices is larger in size and stronger in transverse velocity, and the breakdown of the vortices happens near 0.8 c of the chord. The first layer vortices contribute to the enhancement of momentum mixing near the airfoil surface during the control cycle. Compared to the lower forcing frequency case, the reattached flow is more steadier. As a summary, a synthetic jet actuator array was designed for separation control on the Naca 0025 airfoil, and a synthetic jet actuator are commercially available, so it does not require customer manufacturing. It can achieve comparable control result compared to previous synthetic jet actuator with rectangular jet exit, which Mark Vero has been using. And the forcing of the synthetic jet array, both low and high forcing frequencies, suppress flow separation at low angle of attack. But the flow dynamics is different, and we need further investigation on the mechanism of the reattachment to find why both forcing frequencies can suppress flow separation.